The third application are transformers. And transformers, a transformer is a device that is used to either increase or decrease the voltage. Voltage in the system. And the key to this is that it's the voltage that's changing, it's not the power. So the total energy is not changing, it's just the voltage. And that has to do with in terms of like what's happening with the current. So when we get to the equations of it, hopefully that'll make a little bit more sense, but we're just changing the voltage. So what happens, and I'm going to draw a little picture here of this, and when you get into class, I'll show you some examples too of what it is. A transformer usually has a piece of iron, and it looks like that. So just kind of hollow it out now. And you end up having current, or a coil of wire that goes through one section. And then you have coils of wire that go through another section. And there's a different number of coils. Okay. So it's just two coils of wire that are near each other. It doesn't have to have this iron core, but again, iron amplifies the magnetic field, so it's going to see a larger effect. So this is kind of the visual what you have in your head in terms of our transformers. So what happens with our transformers is alternating current is sent through one of our coils. So AC is sent through one of the coils. And alternating current, remember alternating current is this idea of current that is continually changing directions. So because the current is continually changing directions, the magnetic field associated with that current is continually changing directions. So alternating current is sent through one of the coils, which causes the second coil to be in the presence of a changing magnetic field. And anytime you have a coil of wire in the presence of a changing magnetic field, a current will be induced in that wire. So because the second coil is in the presence of a changing magnetic field, an induced current is created in the second coil. And so that's the order. Alternating current is sent through one of the coils. That causes the second coil to be in the presence of a changing magnetic field. That creates an induced current in the second coil. Okay, so it's step by step by step. And the amount of current created depends on the number of loops in the coil. And that makes sense. If I have more loops in my coil, it means I have more wire that's being exposed to the changing magnetic field. And if I have more wire being exposed to the changing magnetic field, I should have more charges being affected. Okay? So we're going to see that the equations for transformers definitely depend on the number of loops that we have. All right? And again, it's this idea that current is created, but when we look at it in terms of equations, we look at the equations as the amount of voltage that would supply that current rather than looking at the current itself. And I don't know why that is, but it's always looked at, it's the induced voltage that would supply that current, when in actuality, the current is created, not a voltage is created. All right? So, I guess that current is created because there's like a voltage difference there. So let's look at the equations for transformers. And the equation for the transformers is this idea that and I'm just going to write it out and then I'll explain what the terms are. Vs over Vp is equal to Ns over Np. Oh, that's a terrible P. Oh, that's even worse. Okay, so what do these quantities mean? Vs is the voltage of the secondary coil. Vp is the voltage of the primary coil. Primary being, that's the one we send the alternating current through first, and then we induce a voltage in the second coil. And then Ns is the number of turns in the secondary coil. And Np is the number of turns in the primary coil. So that's where that relationship comes in terms of how much wire there is. If there's a lot more wire in the secondary coil, then it's going to have a larger voltage value induced in it. So the one thing that is important to note is that even though the voltage changes, the power of the transformer cannot increase. You can't get more power out of your transformer. And so at best, and when I say at best, I'm saying 100% efficiency, which we all know doesn't exist, except in whiteboard land and sometimes your textbook. So at best, 100% efficiency, the power of the primary is equal to the power of the secondary. That's at best. And if we think back to our circuits unit and we look at the actual equation for power, power is equal to IV. So that would mean that I primary equals V primary. And that should equal I secondary times V secondary.
So I wanted to model a transformer, and so this is basically a plug, and it's got this kind of boxy unit into it, and there's always some electrical specs on this, so I can use a class 2 transformer. It's got its model number. Here it says my input is 120 volts AC, and so I'm expecting that AC to come in at 60 hertz. And it's a 10 watt transformer. And output, my output is 12 volts, the AC, and I've got 500 milliamps. And so you could actually go through and calculate out the power difference. 12 volts times 500 milliamps. So if I can think of that, that's just like 0.5 amps. And remember, power is equal to P equals IV. So I have a current of 0.5 amps times 12 volts. I only get 6 watts. So I input 10 watts and I output 6 watts, and that just tells you the efficiency of this transformer. Energy will be translated in the form of heat with this thing. So if I were to actually open this up, so I've actually broken it apart, and I can take this part out, I can see the mechanism of my transformer. So here's my input of 120 volts, and it goes into these two leads. And it goes into my primary coil here, and my primary coil is insulated from my secondary coil. And you can just tell by looking at this that I've got a difference in the number of coils, and it's wrapped in like this blue plastic, but you can just see the sheer size of this. It's a little different. And there is also this magnetic kind of ring around this, and that again is just to enhance the magnetic field to try to minimize the amount of energy we lose in inducing an EMF here. So what happens is my alternating current goes in through this coil. Because it's alternating current, this has a continuously changing magnetic field. This is now in the presence of a continuously changing magnetic field, so it will create a current to compensate for that. And then we get an output here out of these two leads. Okay, so that is a transformer live. Okay, so here's an example of a transformer system. So this is my primary coil here on the left because it has the input wire and the output wire. And then here is my secondary coil, and my secondary coil is not actually attached to anything. So there's no direct line of current running through this. So just by the fact that there is electricity running through this coil, there's a magnetic field generated this primary coil. So I'm going to put that there. And remember, transformers work with alternating current. So by the fact that there is an alternating current, the magnetic field of this coil is constantly changing directions. So that means the the secondary coil is in the presence of a changing magnetic field. And because it's in the presence of a changing magnetic field, there will be an induced current in this secondary coil. And so I can show the magnetic field in that secondary coil, and it looks like that. And you can see the further I put my secondary coil away from my primary coil, it's not under as strong of an influence of this primary magnetic field. So my secondary magnetic field, or my secondary current, the induced current, actually decreases. So my secondary magnetic field decreases. You can see my light bulb gets dimmer. So there's this limit to how far away, or I'll say how close you need to be in order to actually see the effects of the induced EMF in that secondary coil. Another interesting just kind of application is, we haven't talked too much about this, but it is what is called just like magnetic field, I'll say absorbers or deflectors. So right now there's air. So when I have an air-filled coil, the secondary coil is completely affected by the primary coil's magnetic field. And even if I put this with water, like water does not, it's not a medium that is going to deflect the magnetic field. But I just wanted to show you guys an example. If I put a steel in there, steel will actually deflect the magnetic field so that the secondary coil is no longer in the presence of this changing magnetic field, and there's no longer a current running through it. So kind of interesting application there in terms of magnetic field deflection.